So welcome, everyone. My name is Jean-Robert Thiron. I'm the Vice Director of Research and International Affairs, and I have the great pleasure to say a few words of welcome on behalf of the University of Vienna. We're actually excellent in computer science, especially in the theoretical part. In the applied part, we're working on it. So these are exciting times at the University of Vienna. Just a few weeks ago, I think 4 or 5 weeks ago, the leadership of the University of Vienna had negotiations with the Ministry of Education, and we got the result was we got a huge budget increase, well, huge, 17%, which is, I think, really a remarkable increase we got. In numbers, this means that we have an additional budget to invest over the next 3 years of 207 million euros. We're of course excited about that, to invest this amount of money, and but this is also a challenge. It's a huge challenge for the rectorate, but actually for the entire university, because we will invest this money mostly into human resources, into brain power. So this means we will have to hire lots of people, and of course we have committee work and so on. So many people will be involved in this. So this is a challenge. So we have been very quick. We have been kind of prepared for this additional amount of money we get. And so we will, you can see on our web pages, we will go online on Monday with the announcement of 73 new professorships. A huge step forward for the University of Vienna. So what do we do? Well, we invest in fields that we want to develop, that we think are promising. And as you can guess, data science and digital humanities is one of our top priorities. The reasons, I think, are obvious why we want to invest in these domains. We have a digital change transforms all aspects of the society, of the economy, of our everyday lives. And we, as a university, as a society, we need to get ready to have a sound, as a university in particular, it's our responsibility to have a sound scientific basis to understand and navigate and shape these processes that are upcoming. So what do we do at the University of Vienna? We have initiatives in teaching. So we will start 3 new master programs that are related to this digital revolution, if you like. So one is data science, one is business analytics, one is digital humanities. So these new master programs are thought to educate the next generation to reflect, navigate, and shape these processes. But of course, we also invest in research. And here at the forefront, we have these research platforms that are supposed to build bridges between faculties in particularly exciting new fields. And so one of these platforms for cross-disciplinary research that brings people together from various disciplines is this one, the data science at Uni Vienna, who is organizing today's event. We think this is a particularly exciting and promising research platform. Why do we need data science? Well, I think this digitization has created lots of new data sources, lots of new data. We need to figure out how to deal with these data and what to learn from it. And so to be able to do this, we need the various fields to work together. We need the mathematicians, we need statisticians, we need computer science. And so we will hire 19 new professors to strengthen this exciting field broadly. So on the one hand, we'll have these methods, but on the other hand, we will also have a broad range of applications. And that's also because the University of Vienna is so diverse. So this is really an advantage for us that we can bring together lots of different applications in this endeavor. So there will be applications from finance, for example, digitalization of industry, which sometimes in German is called Industrie 4.0, but also astronomy, medicine. I think a particularly interesting link could be to the digital humanities, where we are very strong in the digital humanities, and so I think that should be a great transmission. Apparently, we're not quite sure what data science really is. So we've started the initiative. We have some ideas what it means. We're very grateful that Professor Gelman will explain to us a little bit what it could mean, or what it actually is. So we do initiatives in teaching and research, as I explained, these new master programs. We invest in research, but we also do third mission. Third mission means to transmit the knowledge to society, to get out and talk to people in a language they can understand more or less. And so I guess that's tonight's event is supposed to be part of this third mission also. So I have had the pleasure to meet Professor Gelman today for the first time and shake his hand and say hello. However, I am a great fan of his research. So I have come across your research in my own research. He's a great expert not only in statistics, and I guess he will talk about statistics later on, but also in political science, which is a field I'm very much interested in. And I came across his work in the context of the so-called paradox of voting. And so this paradox of voting, it's particularly a paradox for economists, I have to say. But the economists say, you know, if it's more likely to be run over by a car on the way to the polls than casting the decisive vote, and it's worse to be run over by the car than, you know, the benefit is of casting the decisive vote, you shouldn't go voting. You know, the cost is higher than the benefit, so, you know, there's no point from kind of the hard-nosed economics perspective. But then it's a paradox because, you know, economics just totally fails to explain this very important phenomenon. People everywhere go voting, and so that's a very important topic. And Professor Gelman contributed very interestingly to this literature. Number one, by showing that indeed it is very unlikely to cast a decisive vote, at least in presidential elections. I think it's about 1 in 60 million, if I remember correctly, US presidential election. So it's very, very unlikely to really make a difference with your own individual vote. But then, you know, it's still somehow, he also argues that it's still somehow rational to do this because, well, it's true that your chance is very small, but if you make a difference, you make a difference for many people. And if you care about that, then it all makes sense again. So it's perhaps more the altruism or these other motives. Could also be an expressive motive, just because you want to do your duty or other things. So, but today is not about political science, as I understand. Today is about data science, and we will learn what it is. So I look forward very much to this event. Thank you very much, the organizers, for bringing this event to the University of Vienna. Thank you, Professor Gelman, for being here. Thank you.
Thank you so much for your nice words. My name is Torsten Moller. I'm actually the speaker for the platform. It's my honor to welcome you all here today for this event. I want to say a couple of words about the platform, how we came about, what we are about, and who we are. I'd like to put names and faces to data. And I'm most excited, one of the greatest news that we have are those 4 people right here. They're our new data science people, PhD students. When we got the funding for the data science platform about a year ago, not quite, that's basically where the money went. And I'm so excited to welcome Lena Bauer. Where is she? Is she here? Hello? Right there. And Mario Pahl, there. And Sebastian, oh, you're all sitting together, of course. And Michael, is he here? He had an accident earlier today, and he went to the hospital. We all wish him well. Not life-threatening or anything, but still serious, so he's not here today. But please talk to them. It's also a networking event. Ask them what they're doing. I kind of want to put a little story to them. When Lena applied, actually her application got lost. And then at one point I got an email from her. It's like, what happened? I haven't heard back. It's like, who are you? And then we interviewed her, and in her interview she started saying, well, I'm actually a barista. And we were like, oh my God, you know, we have to hire you. But that wasn't the reason. So for Sebastian, I have to say that, you know, before he came to interview, he was sitting with Werner Schröttner, our the faculty manager, and they chatted a little bit. And apparently he said, you know, I never thought that I'll be back in these halls again. And it's like, why? Well, I was doing a summer job furnishing this house. And now he's back and actually living in the furniture that he put in. Michael Sedelmeier, I have to say that I had a postdoc just before he started with the exact same name, other than the Y was an I. And he says, yes, I know, often I got email for your postdoc to my email address. And Mario is just a really, really lovely person that you'll find out right away when you talk to him. So please talk to them. We're very, very happy to have you here, so welcome in many different ways. But like I said, there's also many of us that started the platform are here. Here are faces to the names. Please talk to us, get involved in many different ways. But I do want to tell you a little bit about, we're very excited to start off this year's lecture series with Andrew Gilman. I'm very excited about his talk, but it will continue in January. We have Elaine Chu from Queen Mary, University of London. She'll give a talk with a piano. This is going to be really exciting. And so will be the talk by Gudrun Gersman from the University of Cologne, an expert in digital history, that will be talking on April 4th. We will supplement these talks also by local people from the University of Vienna that are presenting their data science challenges in a public forum. So please stay tuned, check out the website, follow us on Twitter or on the mailing list. Vice Rector Turan already presented the really fresh news and exciting news. I'm so excited that we'll be hiring 12 full professors across 8 different faculties in data science, and the call will be out on Monday, as well as 7 tenure track faculty across 5 different faculties. And the call will be out on Monday. I'm so excited about this and the development. I'm so thankful for putting resources in this really important area. There's a lot of stuff happening at the University of Vienna. As already mentioned, we're working heavily on these graduate programs in these different areas together with actually many different faculties that will be involved in them. There's a lot of work ahead of us, and we're very excited. Please get involved in many different ways. We're not an exclusive club. We'd like to have your thoughts, your problems, your ideas, your involvement. There's different ways, give a talk in our lecture series, become engaged in other ways, become an associate member if you're a research faculty or research partners. If you're an industrial partner, we love to work on applied problems. That's what making data science really data science in many different ways. And we're always looking for sponsors if you're interested. We have actually done a whole bunch of stuff already. We had a very successful summer school on deep learning and visualization just this past September. Is there anybody here that took part in it? A couple of people. So I'd like to say that was a lot of fun. I hope you agree. We had over 50 participants from around the world, as far as the US, actually. And it was actually in collaboration with a network called Action between the Czech Republic and the Austrian Republic, the Austrian state. And we will continue this in 2019, so please stay tuned. I'm very lucky, we are really lucky to have the Data Science Initiative by students. I see one of the representatives right here, talk to them as well. They have also an exciting program coming up, an introduction to deep learning on November 20th and 27th, as well as a data science hackathon in March. Check out their website, join their mailing list, and get involved. And last but not least, I'd like to thank a couple of people who made this event really happen. They did a lot of work behind the scenes, and this is Anne-Marie here, and Christian Noll. Could he come? He couldn't, and this person is taking photos over there, Michaela. Thank you very much for your help, as well as actually Kurt Kienast, who's putting together the video recording here, and the wonderful team of the University of Vienna, the PR team that have helped us a lot to put this together. So follow us on Twitter, on the mailing list, stay tuned, get involved. That's the last thing I'm going to say, and then I'll leave the stage for Hannes Leeb to introduce our speaker. Thank you very much.
Right, my name is Hannes Leeb, and I would like to say a few words about Andrew. You've already met him probably in his impromptu lecture he gave just before the talk. But what about himself? Well, after studying at MIT and Harvard, Andrew's career took him to the AT&T Bell Labs, the University of California at Berkeley, the University of Chicago, Harvard, and finally Columbia University. At Columbia, he is currently a professor of statistics and political science, and also the director of the Applied Statistics Center. He's a distinguished researcher, as you've already heard. He's an elected fellow of the Institute of Mathematical Statistics and also of the American Statistical Association. But he's also a consultant for various companies, including businesses like Pfizer, or law firms, or other organizations like the New York State Attorney General's office, including and a writer of statistical software. And last but not least, he's also a very active blogger. He's one of the main contributors to the Washington Post's Monkey Cage blog. And he also maintains his own blog at andrewgelman.com. So in all, I think we are in for a very inspiring talk now, and I leave the floor to you, Andrew.
So I really liked what you said about data science not being an exclusive club. I was a physics major in college, and I like to say that physics is like Brazil and statistics is like Chile, in that in physics, if you want to get to the frontier, you have to study for about so in physics, if you want to make a contribution, you need to sort of hack your way. You have to sort of go out, you get off the beach, you walk a while, long ways, you have to take years, then you're finally at the frontier and you hack your way through the jungle. It takes a long way to get anywhere. In statistics, it's like Chile. You get off the beach and then you're in the mountains already. So really anyone can make contributions to statistics and data science right away using their subject matter knowledge. So it really is a very open field, and I think that's a great thing. It's a pleasure to be here in Vienna. So I noticed all sorts of famous people were here, like Erwin Schrodinger. And I wanted to mention, apropos of that, the relation of the uncertainty principle to statistics. So in physics, the uncertainty principle is that you can't measure the position and momentum of a particle at the same time. So if you have a little electron and you want to measure its position, well, the only way to measure the position of an electron is to look at it, and the way to look at something is to bounce a photon off of it, and then it comes back to your eye and you see where it is. But when you bounce a photon off of something, you add energy to it. Can you hear me in the back? I don't know how it works with this. So to see something, to locate something, you need to bounce a photon off of it, but by bouncing a photon off, it adds energy, which changes the momentum, so you don't know the momentum anymore. Now, you could add a very low energy photon, which won't change its momentum very much. But if you bounce a very low energy photon off of something, you can't locate it geographically because low energy photons have very long wavelengths. So no matter how you do it, you can't win. That's it. What Schrodinger expressed in mathematics. Now, it's similar in statistics. So when we do survey research, just as the electron doesn't truly have a position, it's like that famous cat that's both alive and dead at the same time. If I want to know what your position is on some political issue, you sort of have all positions in your head at the same time. And I can only localize your position by asking you a survey question, and then you'll respond. But by asking you that question, I've changed you. I've added information to you. Now, of course, I could ask a question in a very soft way and add very little information, but then I wouldn't be able to localize your position very well. If I really want to localize your position, then I would need to add a lot of information and ask you a long questionnaire, in which case I've really changed your momentum so much that I can't be measuring it anymore. So this is kind of related, as I talked about in the pre-talk earlier, this is related to a general topic in data science, which is the data and where the data come from. Now, today's talk is about Bayesian workflow. So maybe before going on, I should say what is Bayesian and then what is workflow. So Bayesian statistics uses prior information or external information, or more generally, it refers to statistical methods that combine information from different sources. Now, it is said of statistical methods that what makes a statistical method effective is not what it does with the data, but what data it uses. So when we teach statistics or use statistics, we tend to think of Bayesian methods as a way of getting more out of our data, something we do to the data to squeeze more information from the data. But more importantly, it's more like a way of using more data. So in two ways. One is that by using prior information, of course, we're very directly using more information. So we're putting information in. But in addition, indirectly, when we use prior information, the prior information that we often have is kind of weak. So usually the prior information is not so much that we know this is happening, we know this, we know that. If we already knew it, we wouldn't need to use the prior information. Rather, the prior information we typically have is, I don't think this is very important, I don't think that's very important, I don't think that's very important. By including more prior information, we can do what's called regularization, which means we can include more terms in our models, we can include more complexity to our models, and I'll demonstrate with an example. So it gives us the freedom to put in more. So basically, a Bayesian statistician doesn't have to be, but in practice tends to be a skeptic. It's someone who tends to say, my prior is that I doubt most things are going to work. And the funny thing is that being a skeptic allows you the freedom to explore. And if you come into the world as a naïf and you say, anything I see, I'm going to believe, anything I see that's statistically significant, I'm going to believe, then it's going to turn out that you're going to have to really restrict the range of problems you work on. Because otherwise, you're going to start believing everything. And then you might as well just start publishing a scientific journal. That's kind of a joke, that last thing, because scientific journals publish all sorts of things they shouldn't. So if you believe anything, it's like you're, oh, whatever. So conversely, though, if I'm a skeptic, I can feel free to explore, knowing that it will take more information to to convince me. So skepticism is really, like, in some sense, a pivot. It's a way for us to use more information. So that's Bayesian. Now, what's workflow? Well, workflow is something that it's a popular term now. Like, here we are using GitHub and Trello and Slack and all those other things. Workflow it's one of the slogans that I like. It's a modern slogan. Nobody used to talk about workflow. In statistics or research methods, workflow is somewhere in the middle of the road. So you could say that the first step is examples or worked examples, then comes workflow, then comes method, then comes theory. So as a student, you often start with a theory. You hear about theory, and it's illustrated with examples. Now, as you get more advanced, you realize the theory often derives from the examples. And so we have examples, and they allow us to develop a theory. But it's often there's kind of a gap. Like if I look at my own work, my own books, we'll tend to have the examples in the theory. Say this example motivates a theory, this theory is illustrated by the examples. There's two steps in between theory and examples. There's workflow and methods. So a workflow is what you did. So it's an abstraction of what you did to solve an example. And when you see a statistics paper with an example, like in the applied section of the Journal of the American Statistical Association, we have application papers. Nobody cares about the application. I know this because as a political scientist, when I publish political science papers in the Journal of the American Statistical Association, no political scientist ever reads these things. They don't read the applications for that. And of course, the statisticians have no idea how to judge the political science example. They read it to get the workflow. But because workflow is a relatively new concept for us, we tend not to formalize it. So we give an example, but it's supposed to be read for the workflow, but you have to read between the lines. So just like talking about workflow, it's already in advance. It's already a step forward. And so as we know, I mean, there was a famous researcher from Vienna who wrote a lot about how just talking about things can help you understand things better. So this guy named Sigmund Freud, right? And that's kind of what's happening with when we talk about workflow, that we're not explicit. So after workflow comes methods. So a method is not quite a theory, but it's a set of steps to follow. So I want to talk today about Bayesian workflow in the sense that, like, Bayesian statistics doesn't really mean much without the workflow, and there have been ways in which we've advanced. Does that mic work by any chance? Can you try it first? Yeah. Yeah. Okay. If it doesn't work, it doesn't work.
When you need to use it, it doesn't. No. But wait a minute. Another minute. Wait. All right.
Okay. Fine. Okay. So traditional. What's traditional statistical workflow? Well, it's stuff in the book. So like, we have data Y1 through Yn, IID, Poisson, blah, blah, blah. So that's kind of like the model's already there. But that's not realistic, right? We don't know the model ahead of time. That's what's in the textbooks, right? Like, you see the students here. I have a bunch of Poisson data. What does that even mean, right? Like, you don't, like, that's silly, right? Makes no sense. Then there's what we call the Tukey-esque workflow, which is kind of how we think of things now. You have a data set. You have this data set, and then you have a procedure, and you throw the procedure at the data set, and that's kind of the workflow. Or in machine learning is more sophisticated. You don't have a data set in machine learning. You have a data stream. So data are flowing, and then you evaluate your procedure, right? So machine learning is advanced. It's sort of going beyond the Tukey-esque approach because it has within it a way of evaluation by looking at the errors of your prediction. And one thing that we should also learn from machine learning is the separation of two things. On one hand, there's the model or method, and on the other hand, there's the objective function. So that's similar in statistics if you've learned about bootstrapping. When you bootstrap, you have two things. You have your estimator and you have your bootstrapping procedure. And they're two separate things. So in Bayesian statistics, we have that too, although you might not have heard about this, but we have our model, and then we also have our predictive checking or evaluation. So again, your method of evaluation can be inspired by your model, or your model can be inspired by your method of evaluation, but really they're two different things. And we should, and so that's all modern statistical methods have this bifurcation, this two-facedness to it, which could be said to be an incoherence. So modern statistical methods are all incoherent, which is, I think, kind of necessary. And of course, cognition is incoherent too, right? We talk about the executive function in the brain, making decisions, and so forth. So what's missing, though, from this modern view? There's still something missing, which I'll call multiplicity, and it comes in two ways. The first is fitting multiple models to a single data set, and the other is applying a single method to many different problems. So let me talk about them. So it's fitting many models. So some of this you're familiar with. I don't know what's the right model, so I better fit 10 models and see which fits the best. Or nowadays we do model averaging. So I'll fit 10 models and average them. I'll fit a larger model. Or I might fit 2 models because I want to reject one model. That's not what I'm talking about here. What I'm saying is even if you knew the correct model, you knew the exact model to fit, the true model, or at least the best model in some sense, I would still want to fit multiple models to my data. Now, why is that? Why would I fit multiple models if I already knew the true one? Well, I want you to think about this for a moment. We want to fit simpler models in order to demonstrate that we needed to fit the model that we fit. And we want to fit more complicated models to show that we didn't need those. Right? Well, it sounds sort of like propaganda, but it's not just that. So like, let's take a simple example. I'm doing an observational study. I want to know the effect of some policy. So I compare people who did the policy, people who didn't do the policy. I need to control for a bunch of pretreatment variables. You know, I do maybe I do an instrumental variable. I do all sorts of things. Well, there's no doubt that whatever I do, I should compare to the simple difference. Because you got to say that. You got to say, look, the simple difference is this, and then our final estimate is that. Why are they different? Oh, well, we need to kind of have a trail of breadcrumbs to make the connection, right? We need to say, oh, well, the simple difference was this, and after we controlled for it, it was still there because the two group, or here's the simple, we saw no difference, but then it turned out that it was sick people who took the treatment and healthy people didn't, and after you control for this and this and that, you get a different answer. You need to tell that story, otherwise nobody should believe your results. You shouldn't believe your results. There's no way, because you don't really know that your model is correct, but even if you did know the model was correct, you'd want to go through those steps. Then you want to say, well, what if we controlled for some more variables? Well, I'm going to control for a few more variables, and it turns out not to change the result. But isn't that good to know? You want to know that. So that's part of our workflow, but is it any statistics book? Well, not really, not as a workflow. It's yes?
No, I'm sorry. No, I'm confident. It should work.
Okay, great. Oh, this is so much better. Excellent. Okay, now we're out of time. Okay, so we need tools for understanding. I guess I should. Maybe this is better. We need tools for understanding our models, and again, that's not really in our books. It's not in our theory. So we need to develop theory. Let me tell you a little about the history of statistical theory. So first, theoretical statistics is the theory of applied statistics. And so since we can do more, our theory will develop. But the history of statistics, as I see it, is a gradual inclusion of more and more things into, is it like echoing too much here? Okay, is a gradual inclusion of more and more things that were outside, bringing them into the tent. So if you think kind of way back, like statistics, summaries of numbers for the state, bringing probability into statistics. That was maybe the first thing. Like saying, here we have some numbers, and we can interpret them using things like Poisson distributions. Then if you look at statistics in the age of Carl Pearson, they were very much into categorizing things based on distributions, giving the names of different distributions. This was like a way of thinking. Like, I have a bunch of data, it looks like they follow the normal distribution. Well, there must have been a bunch of small independent effects that could be added up to have reached this. Or my data look Poisson, so therefore this corresponds to random waiting times. Or my data look like a gamma distribution with 2 degrees of freedom, which would correspond to that 2 things had to happen for us to see. Like, what the data look like would tell you a story. But then people moved on, like things like regression models got added into the mix. Hierarchical modeling. So there used to be this thing they would call empirical Bayes, because they would estimate the prior distribution from the data. But that got folded into hierarchical Bayes. It became included. Exploratory data analysis, when Tukey wrote about it, it was kind of considered to be unrelated to the rest of statistics. Like, you either do modeling or you visualize. And in fact, that's still true in a lot of applied papers. People do some visualization, they show you some graphs, then they jump into the model and they never make a graph again. Well, actually, as we've discovered and formalized, the better your model, the more you learn from a visualization, and I'll demonstrate that in a bit. Visualization tells you what you can see beyond what was expected. That's what a visualization is all about. So the more you expect, the more you learn from a visualization. Conversely, by visualizing, we can form better models. So we've incorporated visualization, we call it posterior predictive checking, so it's no longer just good practice, it's also part of our workflow, it's part of our theory. And other ideas too have gone in this. So some of this understanding models, comparing models, is going to require research. Because what I said is you compare many different models and see how your inferences change, but that implies a kind of calculus or language that can connect the models, right? Because what I'm saying is I'm estimating this parameter in a simple model and a more complicated model, and how did it differ? That means I have to be able to say that the parameter in this model has the same meaning as the parameter in that model. So how do I do that? That requires some thought. Now, the other thing is applying a single method to many different problems. So I talked about many models to one problem. So that's very fundamental to statistics. In frequentist statistics, it's called the reference set. And in Bayesian statistics, it's called the prior distribution. It's the thing that you average over. It baffles me that Bayesian statistics and frequentist statistics are considered to be different, because to me they're the exact same thing. The prior distribution is what you evaluate, and all frequentist statistics is evaluated over some reference set. Statistics is said to be the science of defaults. So we never do things just once. We don't solve problems, we develop procedures. How much time do I have left? Oh, I have an hour left? What? Total, but how much time do I have left then? 5 minutes? Okay. So I would sort of like to focus on 2 examples, and then talk a little bit about the future of data science. Okay. So the first example is a study that was done of early childhood intervention. It was a study done about 25 years ago with a bunch of 4-year-olds in Jamaica. So some researchers from the United States came. There were 130 kids in the experiment. Half of them got an intervention, which was the researchers worked with the parents, I think the mother of the child, once a week, gave them lots of advice on how to educate the child. The other half just did null intervention. I guess they gave them some leaflets and some zinc. They gave everybody zinc. That was a big thing like that, giving people zinc. Then they followed the kids up and looked at how much money they made 20 years later. That was the outcome. Though it was economists, so what they said was they measured their earnings 20 years later, because economists have this thing, they say how much money you make, they call it your earnings, which is kind of funny, but that's how they talk. They found that the kids in the treatment group had 42% higher earnings on average than the kids in the control group. So they reported, oh, and was that difference statistically significant? What do you mean? You know, yes or no. What was it? Of course it was. If it wasn't, they wouldn't have reported it. They're not, I mean, you know, they're not going to just report complete noise here. That wouldn't be cool. So yeah, it was statistically significant. It was like a, you know, there was a standard error of about 20 points. So it was somewhere between, the 95% interval went from like 2% to 82%, something like that. So it's a 42% effect. And I don't know, I don't believe that. I mean, well, let's say I think 2% is more likely than 82%. It's hard to increase people's earnings by 42%. I mean, that's kind of a lot. But if you actually think about this study for a minute, by the design of the study, the estimated effect had to be at least 40%, because the standard error was 20%, and they're only going to report something that's statistically significant. And they're not going to do this big study, longitudinal study that takes 25 years and not come up with something that's statistically significant. That would be kind of immoral, right? To do all that work, to waste all the effort of all those people. So you kind of know ahead of time that the effect has to be at least, the estimate has to be at least 40%. So if I were to think, well, I haven't got to the Bayesian workflow part, but suppose that the true effect of this intervention is, I don't know, 5%. Seems maybe it does something, it's possible. So if the true effect is 5% and you do this study, then the estimate you're going to get, it has to be at least 8 times larger than the true effect size, by definition. Well, it could be positive or it could be negative. It's pretty random whether it's positive or negative, but it's 8 times too large. So this is a bit of frequentist analysis. What I'm saying is that if researchers repeatedly apply a certain statistical procedure, they will overestimate any effect size by at least a factor of 8, which that's a biased estimate. But the funny thing is, it didn't say anywhere in the published paper, they didn't say, well, we have this estimate and it's biased by a factor of 8. Well, of course, the bias depends on the true treatment effect, which you don't know, but 40%, like, you don't think it would be that large. So we're using prior information here. It's actually not in a non-Bayesian way, but in this case, what's important is that we're using the prior information at all. And it's funny, though, because the researchers thought they were using an unbiased procedure, but that's because they weren't evaluating the procedure that they were really doing. So in a sense, their theory, their statistical theory was impoverished, right? They were not modeling what they were doing. They were modeling something simpler. So this is an example of where thinking about workflow can help, because if you step back and say, what is their workflow? We gather data, we look around for something statistically significant, and then we report it. That will cause you to overestimate. Now, sometimes people say, well, this is a problem, so what you should do is have a more stringent threshold for statistical significance. But that wouldn't necessarily help, because that would actually increase the factor by which things are overestimated. Now, things are a little bit worse than this, actually, in that there's a feedback loop. So what I just told you about, we call the statistical significance filter, that only large things will appear. Well, of course, you can resolve the statistical significance filter by getting more precise measurement. They could have done a study of 10,000 people instead of just 130 people. But, well, of course, that would be expensive, but also, why would they do that? Because when they designed the study, they thought that 130 people would be enough. Because when they designed this study, they did something called a power calculation, and they determined that they had an 80% chance. I suspect, I don't know exactly what they do, but when people do studies like this, they do a calculation demonstrating that they have an 80% chance of finding a statistically significant comparison. And how do they do that? Well, that calculation is based on an assumption of the effect size. And how large is the effect size? Well, it's something that they estimate based on previous studies. But the previous studies are these statistically significant results which overestimate the effect size. So there's a feedback loop where you think you're finding big effects, you think you're going to find a big effect, so then you get data, and then you find something big, which is what you're expecting to find, and then you keep going. You can sort of loop through that forever, and think that you're finding something when there's nothing happening at all. Or I should say nothing happening, but whatever happening is could be quite small. Now, indeed, the problem, as you can sort of think about from how I described it, the problem gets worse if your effects are smaller or if your measurements are noisy. And I think the effects are typically small. We don't have too many low-hanging fruit in science. In medicine, you're only ethically allowed to study small effects. Like, you don't say, I have this new cancer treatment and I'm going to compare it to the placebo, right? That's considered unethical, right? You would say, I have this new treatment and I'm comparing it to the best available alternative. It has to be small. If it were large, then you wouldn't be allowed to do the study. You'd have to just give people the new treatment. In education research, we compare a new treatment to an old treatment, and the old treatment is best practice. So I'm doing an education study. Well, where am I doing an education study? In some school where people are willing to participate. So there's some enlightened school that's willing to let a researcher go in and experiment on their kids. You compare your treatment to the best alternative. This enlightened school is probably already doing something pretty enlightened as the alternative. In fact, they may be doing your treatment. I mean, it's not like a secret, these education methods. They may already be doing what you're comparing to. So you're not going to be finding large effects. So let's step back. We are studying small effects using statistical methods that can't really estimate small effects with great precision. So what should we be doing? So Bayesian method will help here in that if we have a prior that our effects are small, it will give us more stable estimates. But of course, it's not going to help us learn a lot. If you do a study and you think the effect is going to be small, and the effect really is small, and you gather data, you're going to learn that it's small. Even small effects can be important. So this suggests to me, when we think about data science, that we should not be aiming for certainty or near certainty. That the goal of a study should not be to demonstrate with statistical significance that we've proved that this worked or that this happens. Because we just have to accept that we don't quite know. That, well, it looks like this helped. It helped in this group. Let's see how it helps in another group. Let's gather data. In some way, sophistication takes us backwards a little bit. So instead of saying we do this study and we're going to prove that we've learned something and prove statistical significance, we say we did a study on 130 kids and this is what this found. This is one data point. Someone else should do a study on 130 kids and see what they found. Like, really nothing's going to help us here but more data. In the meantime, try using the new method. Try recording what you're doing. I think we need more of an integration of research and practice. That when we do research, we should be doing research more in the real world. Because the era is over in which you can learn from 130 people and make policy decisions. If you have a great idea, you shouldn't be trying out in 130 kids. You should be trying it out more generally. But then when you're doing that, it changes the quality of your data. I'll get back to this in a bit. But you no longer have clean experimental data if you're working in kind of the real world, in regular schools, not just doing little experiments. This puts more of a burden on our data science to be working with more complex structures. Now, my second example has a different flavor. I'll tell you there's a great kind of moral to the story, which I'll tell you at the end. But first, I'll tell you the story itself. So somebody sent this to me in the mail a few years ago, or in the email. Influence of Valentine's Day and Halloween on birth timing. You know about Halloween here? They do it here? You've heard about it? Yeah, okay. I think someone sent this to me because they wanted me to make fun of it, but I actually kind of liked it. So I'll show you what they had. These graphs are from the paper. They had the number of births. This was in the United States. There's a record of how many births every day. And they had the number of births on, you see the heart, that's Valentine's Day. Isn't that sweet? And then the 7 days before and the 7 days after Valentine's Day. And you can see there are more babies born on Valentine's Day than on the other days. They broke it up into natural and unnatural births. Don't worry about that. I'll talk more about that in a moment. But there are more births on Valentine's Day. And then, on the other hand, isn't that funny? That's Halloween. You see the witch there? So there are fewer babies born on Halloween. So the first thought would be that, like, you don't want to get your baby born on Halloween because it's bad luck, or Valentine's would be great, and so like you pop the baby out. But, you know, it doesn't work that way. Those of you who have babies know. The effect is kind of indirect, that I think they don't induce the birth on Halloween, because I guess maybe some people don't want that, and they are more likely to induce the birth on Valentine's Day. We see a pattern in natural births also, but that's kind of a selection effect. Like, you have fewer natural births on Halloween because they might have induced it the day before. So like and similarly, you have more natural births on Valentine's Day because they're not inducing it the day before, so you have the natural birth instead. So just looking at total births. So I saw this was kind of interesting, it's statistically significant, but I kind of wondered what was going on. I mean, this is only 30 days, and there's 366 days in the year. And I was like, you know, you're kind of vaguely worried about artifacts of some sort, right? Like, you just pick these days. Should it be 1 week before, 1 week after? How do you correct for statistical significance? Should we look at how many comparisons they did? Like, how do you handle a problem like this, right? This is like a lot of papers you see. Like, you see a pattern, it's statistically significant. It kind of makes sense, but if someone told you it's actually just BS, you'd believe that too, right? Like, it could just be something people like found in the data. So there's a principle in mathematics, which is that if a problem is difficult, then you should solve it by embedding it in a larger problem. Have you heard about this? Did they say this? Like, for example, if those of you who studied probability theory, summing an infinite series can be very difficult, but you make a generating function out of it, and then you can actually solve for the generating function, and then it's trivial to sum the series. A lot of things like this in math. So I'm going to solve this problem, which is what's happening in these 2 days, by looking at all 366 days. Okay, so someone sent me that. This is all the days. Number of births by day of the year. Ignore the curves. They're kind of silly, but the data. There's New Year's, July 4th, February 29th. You can see there's Valentine's Day, Halloween. So if you look at this, fewer people born on Christmas. It looks like there might be something going on in Valentine's Day and maybe Halloween, but maybe not, because we see a lot of fluctuation. Now, if you look at this, there's fluctuation. There's about 52 of these periods of fluctuation during the year because, of course, there's 52 weeks in the year. This is data from, I think, 20-year period, but it's not a 28-year period, right? So there's some correlation between date and day of year. So we thought we needed to decompose things in some way. Someone made this graph for me, which I wanted to show you just because I hate it. Well, like, it's very pretty, right? So it allows you to compare, like, what's happening on the 26th of every month, which is like what you really wanted to know, right? Not. Okay. So actually, mostly what you see from this graph is that there are more bursts in the summer, but if you want to know there are more bursts in the summer, you'd be better off seeing this. This tells you much more clear. So I wanted to show you this as an illustration of like a step gone wrong, that like it seems like a very pretty visualization, but it's not answering the question that you want to answer. But of course, wrong steps are part of the story too. So what we ended up doing was fitting a model. My colleague Aki Vetteri fit this model. It's a decomposition of the birthdays into several terms. So first, there's a slow trend. That's the blue curve on the top. So what that's saying is there was a period during the 1970s when fewer babies were being born in the United States. Then there was a little bit of a slow baby boom after that. We also include a fast non-periodic component, which is the orange line. You kind of need that. Things happen. You know, like the queen has a baby and then people think it's cool to have a baby, and then, there's like an economic downturn and people don't get pregnant for a while. There are things that happen which are not purely random. They have a certain time correlation, so we model that. Those of you who want to play at home, the home game of this, we use Gaussian process models with different time lags to allow autocorrelation. Then we have a day of the week effect, fewer babies born on the weekends. And this has to do with scheduled births, that the doctors are less likely to come in on the weekend. They don't schedule them then. If you look carefully, you'll notice that this day of the week effect increases over time. So over the years, this became more of an effect. Seasonal effect, so more people are having babies around September, and which if you subtract 9 months from that tells you that more people are making babies, when it's cold. So make of that what you will. And again, this can vary a bit over time. And then finally, we have these day of the year effects. So we did not put in these days. What we did was we allowed there to be 366 different factors and let the data determine that. Well, actually, we also include, those of you who know a little bit about the United States, we included Memorial Day, Labor Day, and Thanksgiving, which are floating holidays. They're defined by day of the week rather than date of the year. But other than that, that's a complexity I won't go into. And what do we find? So fewer babies born on New Year's, Christmas, Independence Day, these holidays. Apparently people don't like to have a baby on April Fool's Day. It does seem like there's going on more on Valentine's Day, fewer on Leap Day. I think the fewer on Leap Day is really weird. Like as a mathematician, I think it would be cool to have a kid born on Leap Day. I have a friend who turned 13 a couple years ago. Like every 4 years he has a birthday. I think that's the coolest thing in the world, but people don't always think that way. Okay. Now, having fit this, so this is sort of the right answer, I think. And you can get uncertainties about these too. Having fit this, we then fit it to the model to new data. Here, this was 1970 to 1988. So then there was a gap in the data, but then we had a new data set starting in 2000 to 2014. So let's look at the new data. Remember I talked about fitting the same method model to multiple data sets? So now there's again the slow trend, the day of the week effect. The day of the week effects are larger. Look how they were before. They were around 110 to 90. Now they're bigger because there's more scheduled births than there used to be. The seasonal effect has changed a little bit, and I'm going to get back to that. But notice it looked like this before, and here it looks like this. And now here are the day of year effects. And they're pretty similar. Except they're larger. Look at this here. New Year was at 80, and Christmas was at 80, and Independence Day was at 80. Now New Year's at 60, Independence. So now, like, actually, the rate of births is only half at Christmas because more scheduled births. And Valentine's Day and Valentine's Day still shows up, and so does Halloween. And here's September 11th, which is kind of a new time that you don't want to have your kid born, and that shows up in the new data, but not in the old data. So I want to point out some interesting things. So first, you notice there are fewer babies here and more. That has to be, right? Because there's some principle of biology, which is the baby has to come out somewhere, okay? But then there's some funny things in the data, like, look, here's a 2-week period where there are too many babies. How could that be? And here's a period of like a week and a half where there aren't enough babies, right? This doesn't go up as much as this goes down. So how did that happen? Well, what happened was we have information that's not in the model. So we have prior information, which is that the baby has to come out somewhere, right? So our model is that there's a continuous process, and then it's interrupted by delays where the baby is born earlier or later than it would be born naturally, right? But that's not in our model. This is just a bunch of math. We're just assuming a bunch of delta functions, a bunch of effects. And look at something. This is too high. This should really be up there. See, like, this really means that there were more births. There were more births in the second half of September. These are not special day effects, and there were fewer here. So really, that curve should be going up. Well, look at this. You see how it went up and then it went down? So what happened was we fit this Gaussian process model, and when we fit it this time, it estimated the spatial time scale correctly. But when we fitted this one, it estimated too big a spatial time scale, and so it attributed things that should have been here to here. So really, our model, it really should be not using little delta functions or special day effects. It should really be putting in ringing functions. It should really say that there should be a model for the births being shifted. But this is kind of common. Like, we fit models to our data that don't capture all the features we want. Then we check the model fit. So remember I told you about model checking, how important that is, part of our workflow. So here's the raw data. You can't see much from the raw data. When we fit a sophisticated model, then we could see sophisticated problems, right? So that's what you want, right? It's like the, simple model, simple problem, right? Good model, good problems. That's what you want to do. And then we have this horrible thing. Well, I'll show you one more thing. I'm blowing up this last graph. And then someone asked us if we could check the 13th. And look at that. So it's there all along. Every 13th it goes down. Isn't that kind of amazing? It was there, but we didn't think of putting it in. And of course, you could look at Friday the 13th. It's considered to be particularly bad luck. We haven't done that, but you could. So here's something funny. Let's go back to this. Look at the 13th. So this horrible graph actually had information in it. We just didn't think of looking at it. It was there all along. So what I think of the future of data science is solving many problems at once. So maybe think about that study again with the 130 kids. It was an expensive study. They did a lot of stuff. And then what did they do? They summarized it by some regression and some number. But maybe that was a mistake. Maybe they could have learned more from those kids, more of an integration of the qualitative and quantitative study, right? Look how much we learned by going beyond Valentine's Day. I mean, we learned more about Valentine's Day and Halloween by doing this, and also we learned about all these other things. This comes up all the time. Someone came up to me, this was a few years ago, saying they wanted to do a survey to learn about a certain ethnic minority group in the United States. And like, how can we do a survey? This is really tough because you can't reach these people, and if you use a national survey, the minority group is such a small proportion of the national population, you need a huge sample. So my recommendation was, I said, team up with some researchers who are studying other ethnic minority groups. If your group is 2% of the population, get 49 other researchers, each of whom care about 2% of the population, form a consortium and learn together. Right? So we should be able to do that. Big data need big model, because big data are messy data. So big data are not random samples, they're available data. Big data are not experiments, they're self-selected data. And big data are not typically measurements of the construct of interest. They're typically available data that you then use. So again, these economics examples. You might like to measure the value of things, but what you have is the price of things, and it's not in a complete auction. You have partial information. So you have to model that. Now there's a graph that we sometimes like to draw, and this graph is on the x-axis, it's the sample size. And on the y-axis, it's the complexity of your...
What does that graph look like? So when you have no data or very little data, your model can't be complex because there's nothing you can do. I mean, you could fit a complex model to no data using your prior, but there'd be no real point, right? So when you have very little data, you can't do much. Take averages, maybe simple regression. As you get more data, your model can get more complex. You can include more predictors, you can include interactions, multi-level structures. Then, as your data get larger, your model has to start becoming simpler because your computation. And so then you have big data, and you can't even take the average, right? Because the sample is so large. So what we do in our computational research is we're trying to push this forward, because that's where we are with big data, is that we need to fit more of a model, but it's harder to do that. And of course, if you just sort of fit a simple model to big data and you don't make appropriate adjustments, then you'll kind of get the wrong answer. So I do a lot of work in public opinion research, and more and more we use internet polls where you pay people to be in an internet panel, and then they respond to your survey. So we try to make it a representative sample of Americans, but it can't be. We need to adjust for many factors. So we have a lot of data, we have to do more adjustment. If we didn't do that, we'd kind of get the wrong answer. So that puts a lot of computational burden on us. Let me conclude I want to conclude by mentioning sort of research areas where we're trying to do this. So a lot of it has to do with the structures of models and using informative priors. And traditionally, we didn't use informative priors. When we did Bayesian inference, we'd be embarrassed about using prior information. But as I said earlier, by using strong priors that constrain our parameters to be near zero, we can include more information. In particular, we're often very interested in interactions. So we're not just interested in whether the treatment works or how much it works, but we're interested in who it works for, where it works more or less well. But it's the nature of things that our interactions cannot be estimated precisely. So we can't have a high level of certainty about these things. So we kind of have to juggle large numbers of interactions while being uncertain. Now, this brings me to
maybe to me, the most important scientist from Vienna, Karl Popper, who wrote about falsification of models, scientific models, how you can go too far. One concern that we often have in statistics or data science, but in particular Bayesian statistics, is the concern that we've moved beyond falsification, that what we do is we set up a model and we include our prior expectations in our model, and having done that, all we end up doing is confirming our prior beliefs. So we don't want to be in that position. We don't want to be like the pre-Copernicans who kept adding epicycles to their models. And how do we avoid that? So we can avoid that using external validation and cross-validation. A lot of that we can avoid through having a critical spirit and being willing to find problems with our models. So in particular, I don't do hypothesis testing. I don't have a goal of rejecting a null hypothesis, because I actually know that every model I've ever considered fitting is wrong. So to reject the model is uninteresting. But I do need to find out ways in which my model is predicting poorly, or in which my model doesn't fit the data. So when to kind of bring it back into workflow and these examples, to sort of have an openness to Popper's other idea, the open society. For our work to be open to criticism by ourselves and by others, I think it's very important for us to state our assumptions as clearly as possible. And in fact, I think by making more assumptions, we can learn more. And an example, again, that birthday model, there's tons of assumptions that went into fitting that decomposition. And we couldn't have found problems with our model without first making many strong assumptions. Now, at the computational level, though, we really have to deal with the fact that our data sets are becoming bigger and bigger, and our models are becoming larger and larger. And for that reason, I think it's very important to work on statistical methods that we call divide and conquer algorithms, where we fit models separately to subsets of the data and then put them together again. And we've been doing some research on that. Now, just to give you a very small flavor of this, if you divide your data up into 1,000 pieces, because you can't fit all the data in your model, you can't fit all the data in your computer at once, you fit the model 1,000 separate times. There are kind of two concerns, and one concern is that now I'm fitting each of the models to only 1,000th of the data, so it's harder to estimate the model more stably. So we have an idea which is derived from a statistical method, computational method called expectation propagation, in which we borrow information from the other fits in order to get more stable estimates for each subset of the data. But the other thing, which is, I think, a little bit more interesting, is that everything is changing. So I illustrated that in the example with the birthdays. That the pattern for the first 20 years was different than the pattern for the second 15 years. Of course, it differs every year. Another example would be, what's the effect of early childhood intervention, like that Jamaica study. That was done 25 years ago. So what would be the effect today? It would be something different. So in fact, the computational procedure that we do, which is we break up the data into pieces and then try to structure that, is actually very closely to what we want to do anyway for modeling, which is that we actually want to estimate our model separately for different subsets of the data and put them together. And we have something called the Pinocchio principle that we refer to in computational statistics. You recall Pinocchio he was made out of wood, but then everyone treated him like a person and he became a real live boy, right? So similarly, it's quite common that we develop statistical methods for computational reasons but then it turns out that the model takes on a life of its own. So we break up the data into pieces because we can't handle putting all the data in at once, and then it turns out we're actually estimating something separate from each piece anyway, which means that's what we should probably be doing anyway. So sometimes we want to take our computational ideas seriously, because often they do take on the life of their own. They seem to embody what it takes to compute efficiently. Often embodies some deeper statistical idea, and I don't quite understand why that is, but it's perhaps something that some of your new faculty can research. Are there questions? There's a paw up in the air there.
Please wait a minute.
Oh, sure, it works for him.
He's a philosopher, but as a mathematician, I have to say, in probability and statistics, he had said much nonsense.
Oh, who, Popper?
He's not good. Vienna is not good from this point of view.
Oh yeah, no. Popper's theory of probability is terrible.
We have
I
much
agree,
better ones.
Yeah, no. Popper's. When I was a student, I read the English translation of Popper's Logic of Scientific Discovery, and I spent lots of time trying to understand the probability stuff, and that's all terrible. I agree with you. But I think the political philosophy and the philosophy of science is very good, especially if you take Lakatosh's interpretation of the philosophy of science. I've written about that. It's another story.
So we are open for questions from the audience. Just put your hand up and I'm coming to you with the microphone, which hopefully works for the next 5 minutes.
I'll tell you a story while you're waiting to ask. Oh, no, here's a question. No story. You don't get the story. Sorry. I had a story to loosen you all up before the questions came.
I think the story will be more interesting.
Yeah. No. What's your question?
I was going to ask whether you have been, was it surprising for you at how unsurprising the midterm elections were?
Oh, the midterm elections? They were pretty much what was predicted 2 days ago, or 2 weeks ago, or 2 months ago, or 2 years ago. So Americans, we have this two-party system, and there's a lot of polarization. So most people, I wouldn't say most people like their party, but most people hate the other party and vote in a pretty stable way. But there are some people in the middle, and they tend to think that the two parties are too extreme. And so given that Republicans had complete control of the government, these voters in the middle were inclined to vote for the Democrats. In fact, one reason why the Republicans had complete control of government after 2016 was because in 2016, most voters thought that Hillary Clinton, the Democrat, was going to win. So a lot of people decided they would vote for Republicans in Congress to hedge their bets. So they benefited from that party balancing. So the second the election was done in 2016, we figured that in 2018 the Democrats would gain a lot of seats, as they did.
Thank you for your talk. I was very fond of seeing an example of data visualization. And my question would pertain to visualization and how would you incorporate it in a workflow in your data analysis? So as we saw it in the example of the 13th of every month, having a small dip in birth rate. So what would be your recommendation for someone looking at large data sets on what visualization one should try out to gain more insight?
I think of visualizations as model checks, so as revealing things that weren't in the model. So I like to make graphs that show the raw data and the model together, Now, in this particular, I didn't do that in this example. We didn't really, you didn't see any graphs of the raw data because all you saw were averages over all the years. So probably more could be learned than we've already done. But it's mostly it's that visualization and modeling go together. So I think the modelers think of visualization as a big joke, like they make a visualization to decide what transformation to use for the data. And the visualizers think of the modelers as like missing the point because the modelers are so distant. And I think it just goes together, that a good visualization can inspire the model, but once you have the model, like the idea of a residual plot, that's a simple example, but it's really a special case of the general principle of trying to make a visualization that will reveal departures from the model. And I think it's kind of unfortunate that in the literature, the visualization literature often is kind of embarrassed about models. Like Tukey, if you read his stuff, he had lots of models, but he wouldn't admit it. So he would make models and then create visualizations and then kind of erase the models as if the visualizations came from nowhere. And I think that set a bad example for people.
Hi. When you gave your talk about the birthday, I was always wondering, did you take into account that it takes approximately 38 weeks to baby to be produced, let's say it that way? So if you look for the difference between Halloween and Valentine's Day, it's not exactly 38 days, 38 weeks, but I would like to have a look at when the baby was conceived. Did you take this into account?
No, I mean, you could. No, we were assuming that the pattern during the year had to do with when the baby was conceived, but that the patterns of day of week and date were coming from choices of when to schedule a birth. So, I mean, I don't think that, I mean, people do decide when to try to have a baby, and there's also patterns like when people meet, when they get married, so forth. There's a lot of reasons why certain months are more likely than others. I don't think, I mean, my intuition is that like 40 weeks is so far in advance, and there's this like plus or minus 2 weeks uncertainty. So my intuition is that the day of the week and the date of the year effects would not be explained by when people got pregnant. I doubt that. Although, one could put it in a model and see, or you could do a simulation. I mean, one thing that I didn't say in my talk, but maybe I should have, is that I think fake data simulation is a very important part of workflow, and more we're trying to put that in, but it's not so much in the book. So we tend to say, here's some data, fit the data. But like, I think the answer to your question would be set up a simple model, like in which maybe people are more or less likely to have try to have a baby on a certain day, and then say the baby's going to come out 40 plus or minus 2 weeks, and see what happens. But I think that would answer the question more effectively than anything else.
Hello. I want to address the point you said in the middle of your talk that, if I understood correctly, that we should get away from that need to produce significant results immediately and just try to give suggestions and motivate other researchers to do the same study over again with a different sample or with different data. I think the medical state of the art in industry is that we have that need for significant results to introduce new products into the industry. Do you think that we can get away from that, or do you have a solution to how we could build up that new strategy and incorporate it into industry?
I think there should be more of an integration of research and practice. in medicine, one way people get around that is they'll say that they can introduce something new as long as it hasn't been proved to be inferior to the existing treatment. So that's like this non-inferiority. So that's one way of getting around it. But yeah, I think it's, I mean, I don't think it makes sense to wait to introduce something until it's been proved to be better. I think it makes more sense to introduce more things and to have monitoring systems and then try to see how things are working in the wild. Because at least in the US, there's this thing that a new drug is introduced, but once it's introduced, it can be used for anything. So it can be harmful for people who weren't in the study anyway. So it's not even, like even if you were statistically significantly sure and the study was done correctly and they weren't doing any fishy things like, you know, finding healthy people in the control group and convincing them to drop out of the study and like doing stuff like that, even if none of those things were happening, it still like might not work in the sort of off-label setting in which it's being used for a different purpose. So it's like you're trying to get a level of security that you're not going to have. Now then there are things that I know nothing about in the policy direction, like if you allow them to approve more drugs, are there going to be more bad things happening, or like, you know, will companies take advantage of this in some way? That's sort of another story, and if you're worried about adverse events, then it does seem like you want a more aggressive monitoring of new products. I just kind of think that we should be addressing these things directly. I mean, one of my themes in statistics is that a lot of where people are just very used to indirect reasoning because that's what they had before, and I think we can do a lot more direct reasoning. So instead of, if you're saying, oh, I don't want to introduce a drug that's going to kill people or give people like, you know, birth defects, then that's what you should be looking at, you know, or like, but what if if that's the concern, that's the concern. Like now, are you saying we have a current drug and it has a 62% survival rate and I might introduce a new drug with a 61% survival rate? Is that the problem? Like, I don't know. Like I think you want to be more direct. And this whole thing of saying like, it's okay to introduce this drug because we can reject the null hypothesis that it's exactly the same as the old drugs. Like, where is this coming from? Like, who cares? Nothing's exactly the same as anything. So it seems to me very irrational. And like, of course, we do lots of irrational things. I'm not saying, I mean, if, you know, like, whatever, like I'm not saying everything in life should be reorganized in some sort of Napoleonic grounds. You know, I guess it's not so popular here in Austria, you know, whatever. But that, like if you're doing something because it's tradition or because there's good reasons for it, that's fine. But then what are those reasons? It seems like things like the statistical significance is the worst of both worlds because it's purportedly very technocratic and yet it makes no sense. So then it's like, why are you doing it in the first place? Like it's just a rule. I don't think it makes sense.
All right, if there are no more questions, I would like to thank you for coming. I would like to thank Andrew for the inspiring talk and discussion. There's also a buffet with finger food and snacks outside, so please hang around, talk with all of us and participate. Thank you for coming.